So I'm going to talk about how to describe the shape and motion of the heart, which is one of the most important organs in the human body. And as we know that in terms of human anatomy, there are like dozens or even 100 organ systems existing in our body. However, we don't have sufficient data at the moment to look into details for each of these organs. And perhaps one organ that receives most attention in the research community is the face, because the data for the face is very easy to acquire. We can use cameras to take photos, and we can do that for millions or even billions of subjects. And from these facial images that nowadays we already have very mature technology to describe the distribution of the meshes for the face, we can also manipulate different attributes for the face, such as to add identity, add different kind of expression or texture to and hair colors to the face. And this kind of technology is nowadays being used for creating digital avatars and creating videos for the movie industry. However, for other parts of the human body, in the past, it's quite difficult to get such a kind of data in a large scale, and we don't have the equivalent technology to perform similar analysis. For example, for the heart, if we want to take the image of the heart, we need to use cardiac MR, CT, or ultrasound, etc. And most of the data set we were using maybe a decade ago was in the scale of maybe dozens or hundreds. And however, with UK Biobank, it's the first time that we can get access to the image and three-dimensional image of the heart on a very large scale for 100,000 subjects. And that means that perhaps some of the similar technology we develop for human faces, for computer vision, can also be applied to analyzing the structure and the function of the heart. And the first problem we need to address is from the initial input image, which is shown on the left, how can we perform segmentation to generate a structure for different chambers of the heart? So I think that it is a very interesting story that for the UK Biobank is that the collection of the data set is also at the same time when the AI technology is on the boom, on explosion. So I think that if you recall what happened in the past decade, that in year 2011, Jeffrey Hinton and their group proposed this image classification network, which started the explosion of all AI stories. And in year 2015, that deep learning has been applied to image segmentation for natural images. And it is also in 2015 that Paul attracted me to this question: how can we develop similar techniques to analyze images for UK Biobank? And I started to work with Paul, with Chef Peterson, and many other colleagues, either in this room or in the community. And we developed some deep learning models to perform segmentation, and they can be run very efficiently. So just within 10 seconds, we can run segmentation for the heart for different time frames to segment all the 4 chambers and also segmenting other blood vessels connecting to the heart. And also in the similar times that maybe since 5 years ago, that generative AI also becomes a very popular trend in the world. We know GPT, we know some other models that can generate synthetic images. And I also started to look at whether we can use this generative AI technology to understand the distribution of our data. So in the data, we're looking at these shape models on the right. And we have such cardiac shapes, which is moving for 100,000 subjects eventually, that whether we can use some generative model to understand that first, whether we can model such a high dimensional distribution. Second, that whether we can model the influence of different clinical factors such as sex, age, disease, etc., how they influence the shape and motion of the heart. And to this aim, we developed some model which is called Mesh Heart, which is shown here, published this year. And essentially, it has several components. The first component is now our data is this mesh data, which can contain over 20,000 points which are connecting to each other, and how we can describe the distribution of these points. So we can introduce a method which is called geometric deep learning, which is a method that can reduce the dimensionality of point cloud. And after that, if we can learn some features for each mesh using this geometric deep learning method, For the heart, we also have another dimension, which is a temporal dimension. The heart is beating, so we can collect 50 time frames across each cardiac cycle for the UK biobank data. How can we model the interrelationship between different time frames? And here we applied a model which is called transformer. So essentially, a transformer is also a model underlying in GPT. So in GPT, we use transformer to understand the connection between words in very long sentences or even across the context of entire textbook. And here we're using transformer to analyze the interrelationship between the geometrical features across 50 time frames in this sequence. The third component is this conditional encoder, because here, apart from mesh data, we also have all the information from the patients, from the participants, including their sex, age, blood pressure, etc. So how can we model the influence of these conditions, which is this purpose block here, on these mesh data? So we can also add this component at the end. When we build this entire model, we can train it using the mesh data we acquire from UK Biobank. So here, this is just some results to show that it can reconstruct the cardiac meshes very perfectly. And also that once this model is trained, we can also use it to generate new mesh data, which means we can generate synthetic data. And when we generate synthetic data, we only need to use a right hand of this model. And here that the only input is this purple block, which is a condition. So we just need to provide some imaginary sex, age to this model, and then it can generate synthetic meshes, which look like this. So that means that after we train this model to understand the data distribution across tens of thousands of subjects from UK Biobank, we can model the interrelationship between different kind of factors with regard to the cardiac shape and also cardiac motion. And there are different kind of downstream application we can use such models. We can maybe generate a normative reference model for the heart. So what would be the most representative heart for certain age groups? We can use the model to generate that. Also, we can introduce disease factors into such model to understand that if we have some diseases, whether the heart will develop in a different way. And this kind of synthetic disease model can also be used for in silico medicine. So we can add it with some other biomechanical or hemodynamics model to understand whether the blood flow or other cardiac function would change when you have these diseases. And so for my past research, I'm trying to apply all these AI models to the cardiac imaging data, but also I realized that there are a lot of other very rich information in the UK Biobank data from other modalities, including the ECG data, all the health records, and also different kind of text data or information. And another, I think, interesting direction is that how we can integrate this multimodal data into a full picture, into a single framework, so we can understand the difference between health and disease in this large population. So that's all from my side. Thanks for your attention.